দেখতে পাচ্ছ স্ক্রিন?
হ্যাঁ স্যার।
Okay, so basically we talked about we assume the conservation of this representative points in the space because there is no source, no sink, as because the Hamiltonian probably is Hermitian, and there is no imaginary term, maybe that's a purely imaginary term, and that's why what happened? Someone wanted to enter. There's a sound anyway, and therefore there was no source or no sink, and therefore the rate of increase in this has to be whether inflow or rate of decrease would be equal to the flux outside, that is the representative points moving out. Okay, so from that we got the continuity equation like this, and then little bit further use of the canonical transformations we obtained at the relation that d rho dt is del rho del t plus this, and this you can write as a Poisson vector, and this is what is called Liouville equation. And then I asked you to pay more attention on this, to analyze this equation and come out with possible situations under which this d rho dt and del rho del t could be zero. That is what I asked you in the last class. And you see this d rho dt del rho del t, when it is zero, that corresponds to a stationary state because the rho is independent, it does not have explicit time dependence, and therefore that situation will lead to a stationary state situation. However, if it is zero, d rho dt is zero, then this is also zero. Actually, now a couple of things could arise. Number one, with say d rho dt equals to 0. D rho dt is 0 means that rho is not changing with time, that is the number of representative points around a value say p cube, that is not going to change with time. Okay, and that situation could arise for two different cases. One, of course, under del rho del t 0, assuming that it is a stationary state, that rho is not having a explicit time dependence. With that assumption, it could have two things. One, no, it could have one thing, that is the flux is 0. Okay, because rho is not changing with time, explicitly not changing with time. And then if you want to have d rho dt equals to 0, then you have to have the flux 0. Now thus the flux could be 0 for two situations, right? Now I am telling you the situations. Now tell me, you will tell me that those situations correspond to what, corresponds to what should I say? Yeah, you will tell me what state that will correspond to. So I'll give you two situations. I'll give you two situations where the flux could be 0. Okay. For that, let me do one thing. What happened? Yeah. Let me go to a this whiteboard. Now see, suppose that this is one line. Let me have this line. Uh, 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 let me have this line. Okay. Now you can have like this, and you can have like this. This is kind of a tube. Okay. And let's say your say water is moving this way. I think one can use the arrow also. Hey, what is that? Can one use select? What does it mean? Okay, I'm not giving arrow, but you can put arrow at the top. Okay, so suppose something is some fluid, let's say, is moving. Okay, some fluid is moving this way, right? Now think of a situation where suppose the flow is only this way, let's say. The amount that is getting in per unit time, the same amount is getting out per unit time. Okay, this is the situation number one. And the second situation is nothing is going in, nothing is going out. Okay, these are the two situations I am going to talk about. The flux could be zero in both cases. Again, I repeat, the flux zero. So del rho del t equals to zero corresponds to a stationary state situation. Okay. So under the stationary state situation, I can think of two situations where the flux is zero. Okay. Now, number one situation, flux is zero when the amount of flow that is getting in is the same amount is getting out. Okay. So flux is zero. This is the in flux and this is the out flux. So net flux is zero. And also it could be that there is no flux in, no flux out. And that also corresponds to what happened? Why these sounds are coming? Okay. So that also corresponds to a situation where the flux is zero. Okay. So could you see this one? This figure?
Yes, sir.
Yes, sir.
Okay. So you understood two situations could happen, right? If I want to have the flux zero, right? Now, can you tell me which those situations have some particular names? What are those? Do you know that? Nandini? Are you around, Nandini?
Yes, sir.
You বলতে পারবে দুটো সিচুয়েশন কি?
না, না।
Okay, all right. The situations are, so basically I can say that one situation is rho v is zero, means nothing is flowing, that corresponds to no flux, and rho v is constant, whatever is getting in, that is what is getting out, and this corresponds to a steady state. তোমরা জানো যতটা হিট ঢুকছে ততটা হিট বেরিয়ে যাচ্ছে, it's in steady state, and that is what the practical you did, in Lee's method, right, to find the thermal conductivity of insulating material, ebonite or something like that, right? So you know the steady state. What is steady state? The amount you put in, the amount you take out, then that corresponds to a steady state situation. Okay, under the stationary state, this is a steady state situation. But another situation where rho v is zero means nothing is getting in and nothing is getting out, and that corresponds to a equilibrium state. Okay, so under the stationary state, there are two things. One could be steady state and another could be in equilibrium state. Okay, now in both the cases, whatever the case could be, in both the cases, d rho dt equals to zero because flux is zero and stationary state del rho del t is zero, and therefore d rho dt is zero, right? D rho dt is zero means, what does that mean? That means the density number of representative points around any P and Q in a unit volume around P and Q is constant with time. Again, I repeat, number of representative points in a unit volume around the point PQ is constant with time. That's not changing at all. Okay. So that is what it means, the situation. So in equilibrium situation or in stationary state situation, the rho is constant. And yet another way of having that, this rho h Poisson bracket or commutator in quantum mechanics, this you obtain from the flux term, right? And this one you could make rho is 0 in one way, that rho is 0, but that is absurd, rho is 0. Or you could make rho itself is a function of the Hamiltonian, right? Or rho could be constant. It could be rho could be constant also. Oh, so one way is rho could be constant, then also it is 0. Or it could be that rho itself is a function of h, right? Then that could be another thing. And of course, that will come in the canonical transformation that we'll talk about when rho itself is a function of the Hamiltonian. Then also this becomes 0. Okay. So eventually what we conclude is that in the stationary state situation, the rho, number of representative points per unit volume around the phase space point PQ, it is constant. Let's see what we are talking about here. This means that we are dealing with a swarm of representative points which are uniformly distributed over the relevant region of the phase space. In other words, the ensemble of systems are at all times uniformly distributed over all possible microstates. Then the ensemble average of the quantity f, which could be a function of p and q, is f p cube. Rho is constant, right? But this is the density of representative points, and f is the value at the point p and q. So this is the value in a unit volume, and this is the value in the volume d omega, and then integrate over the entire phase space, divided by, you normalize by this rho d omega, integration over omega. And since rho is constant, you can take rho out here, and this is this, and you can take rho out from this integral also, and rho cancels. And if you integrate over, this is nothing but the total phase space volume, and therefore your f average, the quantity f average is 1 by omega integration omega f of q p d omega, where omega is the allowed or accessible region of the phase space. And that region, the region allowed in the phase space, that depends on the restriction on the energy you are allowing, right? And of course, the physical volume. It is thus clear that in this case, that any member of the ensemble is equally likely to be in any one of the various possible microstates. This is nothing but the postulate of equal a priori probability. The corresponding ensemble is referred to as the micro-canonical ensemble. তোমরা জানো যদিও এগুলো, বাট মনে হয় আরো একটু মোর ডিটেলে হয়তো বলা হচ্ছে। No microcanonical ensemble. In this ensemble, the microstate of a system is defined by the number of molecules n, the volume v, and the energy E. However, as I said earlier, that our previous discussion suggests that we can as well prefer to have an energy range from E minus half delta to E plus half delta instead of a fixed energy E, okay, that we have seen earlier. Now, as the number of microstates does not differ much, we retain the a priori probability postulate, that is, all the microstates within the allowed region of the phase space are equally probable. Then the representative points of the ensemble have a choice to lie anywhere within the hypercell that I was talking about. As I said, the allowed region of phase space should be bounded by this, and therefore that will correspond to the hypercell. So in the hypercell, all the representative points are equally probable. We adhere to that condition. Okay. Now the volume of the phase space enclosed by a hypercell bounded by the equation 14. Equation 14 means the E is ranging from this to this. We have talked enough about this. Is given by this. This prime indicates that the allowed region, the region bounded by this. Okay. So you are integrating over the allowed region of the phase space. Obviously, this indicates the integration over the region bounded by the equation 14. Now, naturally, omega will be a function of n, v, e, and delta, right? Now, because your limits will be accordingly placed, and therefore these things will appear. Now, the microcanonical ensemble is a collection of systems for which the density function rho is at all times given by rho qp equals to constant. As I said, it is constant for this range, otherwise it is 0, right? Because otherwise, beyond that, you don't have the phase space, valid phase space, right? Because system cannot go, particles cannot go beyond this, and therefore this is the region where your density of representative points is constant. That is what I have written here again. Now, accordingly, the expectation value of the number of representative points in a volume element d omega in the relevant hypercell of the phase space is simply proportional to d omega. That is obvious, right? It should be proportional to d omega. In other words, because density is constant, so it will be multiplied by the volume, right? So the representative points in a volume element d omega hypercell, of course, is simply proportional to d omega. In other words, the probability of finding a representative point in a given volume element is same as that of finding the representative point in an equivalent volume element located somewhere, anywhere within the allowed hypercell. Okay. Now, since the ensemble under study is in the stationary state, the ensemble average of a physical quantity f must be independent of time, as I said. Hence, taking time average after thereafter will not produce anything new. We have also discussed all these things. Okay. Just kind of repetition. F average is the ensemble average of F, is the time average of the ensemble average of F. These are same, and as the process of time averaging and ensemble averaging are independent, the order could be interchanged. So ensemble average of the time average, and so on. Now, the time average of any physical quantity taken over a long time must be the same for every member of the ensemble. If the time is not long enough, then the time averaging would correspond to the average over a subset of microstates. Then you may not, if your time is not long enough, maybe probably you cannot get the exact result that you obtain in experimentally. You may not get the exact result. Okay, hence F average is a time average of F over a sufficient long time. Sufficient long time means it can explore all the phase space, entire phase space. That means you take the weightage over all possible microstates. That is what it means. And therefore, that is what, if you take over a long time, then that will correspond to the experimental result. And that is what is nothing but the ensemble average of F, where of course ensemble has to be very large. Okay. Now, next we try to build up the connection between the mechanics of microcanonical ensemble and the thermodynamics of the system. Now, by this time, we have developed a sense that the total number of microstates is connected to the volume of the phase space. In fact, the number of microstates is proportional to the allowed volume of the phase space, and it motivates us to conclude that there must be a fundamental volume of the phase space which will correspond to a single microstate. Now, if the number of microstates corresponds to is proportional to the volume of the phase space, then definitely kind of sense develops that probably there should be a kind of fundamental volume of the phase space which will correspond to, and also they are equally distributed, homogeneously distributed over the phase space, and therefore there must be, it's a kind of what should I say? You can apprehend that could be fundamental volume, little volume in the phase space, which might correspond to a single microstate. And therefore, if it is true, then we have to find out. Okay, first we have to find out if it is true, if there is a little volume, fundamental volume in the phase space which correspond to a microstate, then you can easily simply calculate the total phase space and divide by that fundamental volume and get the total number of microstates, and from there you can connect it to the entropy and hence the thermodynamics. Let us see. That is what it is. Whatever I said is given here. Then this gamma is a number of microstates equals to omega by omega naught. If this omega naught is treated as the fundamental little volume, which will correspond to 1 microstate, and therefore S is k ln of this tau or gamma k ab ln omega by omega naught, and from the relation omega is of course integration d 3n cube d3n p. And we understand that omega naught must be the nature of angular momentum. Of course, I mean this is the product of r. R cross p is nothing but angular momentum, right? And you see here q and p, and therefore the dimension wise this is nothing but the dimension of angular momentum, right? And that raised to the power thrice n, of course. So in fact, we will show that, and I'm sure that all of you are quite aware of the fact that omega naught in n particles in 3 dimensions, omega naught is h to the power 3n, where h is a Planck constant. But again, even though it is quite well known to you, we'll still prove that this omega naught, for this case, n particles in 3D, the 1 microstate will correspond to a volume omega naught, which is nothing but h to the power thrice n. Now, what is the dimension of h? Monojit?
হ্যাঁ স্যার, বলছি স্যার এইচ এর স্যার ইউনিট হলো স্যার জুল সেকেন্ড। এবার স্যার জুল স্যার এনার্জি, তাহলে এনার্জি যদি হয় স্যার এম এল স্কোয়ার টি টু দি পাওয়ার -1
ml square. Now, what I'm saying that h, what is the unit of h? Means what does it represent? It is with velocity or acceleration or energy or what? That is what I'm saying.
স্যার এইচ ইজ কল্ড স্যার প্ল্যাঙ্ক কনস্ট্যান্ট।
I share the jam file with the meeting. Eta ki? Imtiaz? No. Eta you. I shared it with them. What is that? Jam board. Oh, okay. Video chole gelo. Imtiaz? Ki chole gelo? ইমতিয়াজ কি বলছে ভিডিও ইমতিয়াজ
আপনি স্ক্রিনটা প্রেজেন্টেশনে চলে গেছিল বলে বলছিল হয়তো।
ও কিন্তু ইমতিয়াজ আছে তো? হ্যাঁ, মনোজিৎ এবার চলো, মনোজিৎ বলো।
স্যার বলছি ওই ফটোইলেকট্রিক এফেক্ট থেকে স্যার আমরা পেয়েছি যে ওই এইচ ইকুয়াল টু স্যার স্মল প্যাকেজ অফ স্যার এনার্জি, স্যার দ্যাটস কল কোয়ান্টা।
সেটা তো এইচ নিউ। আচ্ছা, তোমরা যখন করো আর কি, ধরো হাইড্রোজেন অ্যাটম, ওকে, হাইড্রোজেন অ্যাটমে যখন তোমরা LZ অ্যাপ্লাই করো তখন কি পাও একটা স্টেটের উপরে? জেড কম্পোনেন্ট অফ অ্যাঙ্গুলার মোমেন্টাম যখন তোমরা অ্যাপ্লাই করো, বা রাদার তুমি যদি এল যদি অ্যাপ্লাই করো, বা এল স্কোয়ার অ্যাপ্লাই করো, তো এল স্কোয়ার LZ এগুলো তো গুড অপারেটর নাকি?
হ্যাঁ।
আচ্ছা, LZ অ্যাপ্লাই করলে কি পাও ওই স্টেটের উপরে?
MH স্কয়ার।
এম
হ্যাঁ স্যার, MH ক্রস।
এইচ ক্রস, এইচ ক্রসের মধ্যে ধরো এটা তো টুয়াইস পাই একটা নাম্বার, তাই তো? m is also a number, right? তাহলে it is proportional to h, so it corresponds to angular momentum. অ্যাকশন গুলো তোমার দেখো না যে h এর সঙ্গে যায়, ডেল্টা x ডেল্টা p।
হ্যাঁ স্যার, হ্যাঁ স্যার।
হ্যাঁ, তো r cross p না, r cross p is a angular
Yes, sir.
momentum, right? So that is what I was asking you. Actually you should have told that this represents the angular momentum. Okay, all right, so angular momentum to the power 3n, that is what I already discussed. Again I asked you the question anyway. Now I guess you all know that for n particle in 3 dimension, the fundamental volume corresponding to 1 microstate is h to the power 3n. So how many of you, is there anyone who didn't know this? Is there anyone, can you tell me who didn't know this? Monojit?
হ্যাঁ স্যার বলুন।
বলছি তুমি কি এটা জানতে যে তুমি জানতে যে এইরকম একটা ফান্ডামেন্টাল ভলিউম এক্সিস্ট করে?
স্যার হ্যাঁ স্যার, এটা স্যার পড়েছি স্যার।
আচ্ছা আচ্ছা আচ্ছা। লামা, উর্গেন লামা, আর ইউ দেয়ার? Lama? Urgen Lama, yes, you are there. Lama, unmute yourself. Urgen? Salini? Salini, are you around?
Yes, sir.
Oh, yeah. So did you ever go through, I mean, have you ever gone through this kind of fundamental volume earlier?
Sir, can't remember.
Can't remember. Okay, okay. I think you have gone through, but probably you don't remember. Anyway, let's look at it. So now see carefully, okay? If you have forgotten, just see carefully. In order to prove that this omega naught is this, for this case, it is not that for all cases it will be h to the power 3n, right? It is for n particle in 3 dimension. Let us consider a classical ideal gas composed of monoatomic particles. Now, in the microcanonical ensemble, the volume omega of the phase space accessible to the representative points of the system is given by d cube 3n, dp 3n, and then you integrate it over the region of the phase space. Okay, that means, you see, if you integrate over d cube to the power 3n, basically dq1 to the power d cube q1, d cube q2, d cube q3. This way you will go up to d cube qn, right? So then if you integrate over, if the physical volume is v, then each integration, there will be 3n integrations, right? There will be n integrations, right? In 3 dimension, and each integration for the real space will give you v, and therefore n times you will have integration, it will be v to the power n. So you take this v to the power n out, and you are left with only d to the power 3np. Now this p, of course, it cannot be anything and everything. It has to be bounded by such that this sum over this is the energy, right? Kinetic energy, because there is no potential. You have a classical free gas in the container. Only you have the kinetic energy. That energy is bounded by this and this. Okay, so your integration will range only in this region. So p will range from this to this.
স্যার
Okay? Huh?
হ্যালো
বলো। হ্যাঁ বলো।
স্যার ইন্টেজ জয়েন করতে পারছেন, একটু অ্যালাউ করতে বলছো।
ইমতিয়াজ, ও কই, আমি তো কিছু দেখতে পাচ্ছি না, কি করে কি করব? হাউ ডু আই ইমতিয়াজ, হাউ ডু আই হেল্প হিম অ্যাকচুয়ালি? হাউ ডু আই ডু দ্যাট? আমার কাছে যদি আসে এটা জয়েন মিটিং এর মিটিং ডিটেলস, অ্যাটাচমেন্ট এটা কি, এটা তো পাঠিয়েছিলাম, বাট ওকে বলো এক্ষুনি আবার রিকোয়েস্ট দিতে, ওই ইয়েটা ক্লিক করতে। অটোমেটিক ঢুকে যাওয়ার কথা গো, হয়তো নেট কানেকশনে ঢুকতে পারছে না, জানো তো। ইমতিয়াজ আউট অফ ক্লাস স্যার, প্লিজ জয়েন ইন। কিন্তু আমি কি করে জয়েন করাবো ওকে? ও তো অটোমেটিক জয়েন করতে পারবে, ওর নিশ্চয়ই নেটের প্রবলেম আছে। হুম, তাই না বিপ্লব?
একবার জয়েন হয়ে গেলে তারপর থেকে আপনা থেকে অ্যাডমিট
স্যার
পাওয়া
তাই
যায়
হবে।
আর
হ্যাঁ,
দুবার
ও
করতে
ও
হবে না।
হ্যাঁ, সেই তো, এক্স্যাক্টলি। নেটের প্রবলেম আছে। আচ্ছা, ইমতিয়াজ বলে আমাকে হোয়াটসঅ্যাপ
স্যার কন্টিনিউ করুন।
হ্যাঁ এক মিনিট। ইমতিয়াজ লিখেছে, আমি লিখে দিই, ইট ডাজ নট require my permission, require my permission. You may have net problem. Okay. So basically, so your integration limit will be dictated by this. Okay. So now if you assume this as y, then y square should be, then you have to multiply with twice and there, twice and there. So in this range. Okay. Now you see, then it should be the v to the power n into volume of the hypercell, because the cell is bounded by this, right? This and this. Hypercell of 3n dimension and bounded by two hyperspheres, because if it is r square, then square root of this is the radius, square root of this radius of radii, this and this. Okay. Then how do you get that? Now, of course, the width that you assumed, right? Because you did not, you are supposed to take a fixed energy, but for practical purpose, we did not take a fixed energy because it does not make much difference if we give a width delta around the fixed energy, and therefore that delta has to be very small, right? Because we are just having a width, small width around the E, therefore delta is much smaller than E. We are assuming that. For that, the thickness of the cell is of course R1 minus R2, right? That means square root of this minus square root of this, and that turns out to be, if you can do the calculation by yourself also, so you just please check this one, okay? That you check that the thickness of the cell is this. Please do it in your notes, okay? In pen and paper, you do this and check and tell me yes, it is correct or not. So you have the two hypercells, one of radius this, another radius this. I am asking you to find out the thickness, where this delta is the energy weight. Okay, so you are asked to get the thickness of the hypercell bounded by two cells, one of radius this, another radius this. Please do it by yourself.
স্যার করলাম, এটাই আসছে।
এটা আসছে, ওকে। আর কে করেছো? এটা কি মৌসুমী বললে?
হ্যাঁ স্যার, মৌসুমী।
ওকে, আর কে করেছো?
হ্যাঁ স্যার, এটাই আসছে।
কে?
হ্যাঁ
স্যার,
স্যার, এটাই
অভিনন্দন।
আসছে।
তাহলে এটা আছে।
Okay, good. Okay, many answers I
Huh.
got. Fine. Thank you. Now, now you see that you are getting this omega is like this, and then what you should have? You should have v to the power n, then the thickness into the surface area of three-dimensional sphere of radius this. So you are having a sphere in the middle of these two, in the middle of the two boundaries, right? One is E plus half delta and E plus minus half delta. So you are on the average. Okay, you are taking the surface area of the cell which has the average radius, right? Or the radius of this, and then multiply by the thickness, you get the volume of the momentum space, and you already have the integrated out the real volume, I mean the real space volume. Okay, so this is what is the total volume of the phase space which is allowed for the system to be evolved, right? So this is the allowed phase space region for the system for the given parameters. I should say this way. So this is the allowed phase space region for the system with the given parameters. Okay, with the given macroscopic values. Okay, that is V, N, delta, and so on. E. So this is what? Now this you know, right? We have already calculated the volume of a sphere of d dimension, right? We have already calculated, and this is a sphere of 3n dimension, and then that volume, and then probably you take the derivative of that, you get the surface area, right? So if you recall that, so this is the surface area of the hypersphere of radius this. So this is the total, and do little bit of rearrangement, because you have 3n minus this one, then you have E here, you have E here. If you just take into account these together, then you will have, you can write this omega. This is the allowed phase space region as V to the power n delta by E twice pi me to the power 3n by 2 by 3n minus 1 factorial. Okay. Now, so this is the, so much you did to get what? To get the allowed phase space region for the given macroscopic parameters n, V, E, and with delta. Given that, you have obtained, of course, yes, with that you have obtained the allowed phase space region for the system, and that this is this. Now you recall the number of microstats. You go back to earlier notes, and we already calculated for such a system. We already calculated the number of microstats. Number of microstats for a system having volume V, number of particles N, and mean energy E with a width delta. Okay, that we have already calculated earlier, right? Sigma, tau, gamma. Mostly, do you remember that we already calculated the number of microstats for these macroscopic parameters?
Yes, sir.
Okay, so this is the value. If you go back, then you will see this is the value we obtained. Okay, I have just noted down from there. I have recalled that. Now, if this is the total number of microstats, and if this is the total phase space volume for this case, then the volume for each microstat should be omega by tau, and that is what we have said here, that omega naught equals to omega by tau. And you do the calculation by yourself right now. Please do the calculation right now and find whether this omega by tau, it turns out to be this or not. So you get the value and tell me if you did it, if you got it or not. Okay.
হ্যাঁ স্যার এটাই পেলাম।
Okay, all right.
হ্যাঁ স্যার পেলাম এটা।
Good. But there is no male voice. Why? Only girls are talking. How about the boys? This is good. I'm I'm not discouraging. This is very good actually. But how about the boys? Why you are silent? Didn't you do?
হ্যাঁ স্যার ওটাই আসছে।
Okay, Biplab.
হ্যাঁ স্যার।
Next.
হ্যাঁ স্যার ওটা আছে।
স্যার এটাই আসছে।
Where is Abhishek?
হ্যাঁ স্যার।
না চেয়ারে হেলান দিয়ে ঘুমোচ্ছ?
না স্যার।
আচ্ছা, ওদের বাড়িতেই তো নাকি? বলছি
হ্যাঁ।
বাড়িতেই তো? আচ্ছা
হ্যাঁ
আচ্ছা, বাড়িতে বসে বসে পড়তে কেমন লাগছে, মানে শুনতে বা ইয়ে করতে?
স্যার বসে বসে শুয়ে শুয়ে ভালোই লাগছে।
ভালোই লাগছে না? নিজের অ্যাম্বিয়েন্সে আছো, যখন যেটা মনে
হ্যাঁ,
হচ্ছে
হ্যাঁ।
খিদে পাচ্ছে মাকে বলছে মা এটা দিয়ে যাও ওটা দিয়ে যাও। হ্যাঁ,
হ্যাঁ,
ভেরি গুড। So basically, so this is what is the now this n. If you have say n1 number of particles, then of course the volume should be h to the power 3n1. If you have one particle in 3D, then it has to be h to the power cube. If it is a particle, one particle in 2D, it should be h square. And if it is one particle in 1D, it has to be h, right? So this is basically total number of degrees of freedom, right? So for n particles, n into 3, okay, 3n. Now, therefore, we may conclude that the total number of microstates is equal to the phase space volume divided by h to the power of number of degrees of freedom. And that is what I said. This will also help us to calculate the density of states of free particles. Well, say with this idea, because microstate is is nothing but the but a state, right? Allowed state, right? Then you can calculate density of states means number of allowed states, okay, for free particles. How? Now let us consider a free particle that I have already. I think I did this thing in your solid state class in sem 5 probably, or sem 6. I don't remember. Now, the free particle in 3 dimension, you see number of states in an elementary phase space d cube p is this, right? Because h cube is a single particle in 3 dimension, free particle 3 dimension, and therefore h cube should be the fundamental volume for a microstate, allowed state, and therefore so many states in the elementary volume, this in the phase space. The total number of states should be gp dp. What? gp dp is the number of states in the momentum range from p to p plus dp. So I name this as gp dp, okay? And then if you integrate over, you get the total number of states, and that should be equals to, if you integrate over the entire phase space and divide by h cube, you get the total number of states, and that is what is integration gp dp. We want to find gp, that is the density of states per unit volume, per unit at p, actually that is what we want to find. Then you integrate out v, so v by h cube integration d cube p. Now probably in here, okay, okay. So this is what is the total number of states. This is the number of states in the range p to, I mean, this is the this total is the number of states in the range p to p plus dp. Then integration gp dp equals to v by h cube, and this is, you know, d cube p. If you integrate over, it will of course give you a volume, 3-dimensional volume, 4. It will give you d cube p. You can break it as 4 pi p squared dp, right? So you have written it here, 4 pi p squared dp equals to 4 pi, you take out 4 pi v by h cube, then p squared dp, and you know the relation, dispersion between dispersion relation for free particle is p square by twice m, therefore p square is 2me. And generally when you talk about the density of states, generally you write in terms of the density of states as a function of E, okay? So then p square twice p dp is m, p dp equals to m dE, and from there you can find dp in terms of dE. Again, p you can replace in terms of E, square root of twice me, and if you put these values here in this, then v by h cube, 4 pi v by h cube twice me, because p square is twice me, and dp is m dE by this. And if you do a little bit of katakuti, then you get 4 pi v by h cube, this m, this, and then this factor e to the power half and dE. And now since it has become function of E and dE, so you can write it as integration GE dE, because if you integrate over, GE dE is the number of states between the energy E and E plus dE, and then if you integrate over the entire energy range, then you get the total number of states, and this also total number of states. And then if you just take the integration out, basically if you make the integrand equal on both sides, then GE is nothing but V by H cube twice m to the 3 by 2 e to the power half, right? This is the your density of states for a free particle, for a single free particle. Okay, and if you divide by this V, actually this is not actually called density of states. Density of states is called when you divide by V actually. Okay, so this is the number of states in the entire system in the range this is the number of the states in the entire system in the range of energy E to E plus D, and GE is the number of states, allowed states with energy E for the entire system. And if you divide GE by V, then this is what is called the density of states, number of states per unit volume with energy E, and that is what equals to twice pi by H cube twice m whole to the 3 by 2 e to the power half. Okay, and density of states of a free particle goes as e to the power square root of E. Okay, now if you have n particles, now I give you a homework. Generally that kind of question appears in NET or GATE exam. N free particles, you have the system of n free particles, then try to use this idea of fundamental volume and find out the density of states for n free particles in 3 dimensions. Write down the problem, okay? আচ্ছা, এই হোয়াইট বোর্ডে ইয়ে করা যায়, টাইপ করা যায়? Can one type here? একটু এক্সপ্লোর করে দেখো তো। So basically what I'm saying is find the
হ্যালো স্যার, যে টেক্সট বক্স আছে ওইটা নিন,
কোনটা টুলবক্স
কি
টিটা?
লেখা আছে?
হ্যাঁ, ও
হ্যাঁ হ্যাঁ হ্যাঁ,
yeah, good. Thank you. Find এই বাবা, এটাকে আবার ছোট করতে হবে প্রচুর। I normal find now using the concept of fundamental volume of the phase space corresponding to a microstate, find the density of states of n particles, free particles, in 3 dimension. এক নম্বর হচ্ছে 3 dimension, 2 নম্বর 2 dimension, আর 3 নম্বর okay. So this is the problem you should work out. Okay, so using the concept, this is n using the concept of fundamental volume of the phase space corresponding to a microstate, find the density of states of n free particles in 3 dimension, in 2 dimension, and in 1 dimension. Okay, বিপ্লব এগুলো করো। এখন n ডিমেনশনটা আমাকে করে দেখাও তো, প্রথমটা n particles in 3 dimension, n figure density of stress টা বার করো তো। এটা লিখে নিয়েছো তো, বেরিয়ে যাচ্ছে এখান থেকে। হ্যাঁ লিখে নিয়েছো? হ্যালো হ্যালো,
হ্যাঁ স্যার লিখে নিয়েছি।
আচ্ছা হ্যাঁ এবার ওটা করো তো, প্লিজ ডু ইট, find it for 3D and later we'll see the others. আচ্ছা আমি তো করেই দিলাম নাকি ওটা, না করে দিলাম না করিনি, না হয়ে গেলে বলবে। হ্যাঁ বলছি এরপরে কি ক্লাস আছে? এরপরে কোনো ক্লাস আছে তোমাদের? হ্যালো, বলছি তোমাদের কোনো ক্লাস আছে এরপর?
না স্যার নেই।
আরে এই এতগুলো ছেলে পুলে রয়েছে, মুখ দিয়ে কথা বেরোয় না কেন আমি বুঝতে পারি না। থ্যাংক ইউ মৌসুমি। কি রে ভাই, অদ্ভুত ব্যাপার। কি অফিসে কি করছো, ঘুমোচ্ছ অভিষেক?
হ্যালো স্যার।
হ্যাঁ, হোয়াট আর ইউ ডুইং ম্যান? ক্যান্ট ইউ সে ইয়েস অর নো?
হ্যাঁ স্যার, আমার বেরিয়ে গেছিল আমার। আমি এক্ষুনি আবার নতুন করে জয়েন করলাম।
হ্যাঁ তোমাদের ক্লাস আছে এরপরে?
না স্যার।
ওকে, দেন ডু আর ইউ ওয়ার্কিং অন দ্যাট, দ্য প্রবলেম আই গেভ ইউ?
সে এখনো হয়নি।
না করছো তো, না করছো না?
হ্যাঁ স্যার করছি।
করো।
স্যার
বলো।
স্যার বলছি
কে
ওই
কে বলছো? মনোজিৎ, হ্যাঁ বলো বলো।
হ্যাঁ স্যার, স্যার বলছি ওই ইন্টিগ্রেশন d টু দি পাওয়ার 3n p
হুম
ওটা স্যার মানে ওটা কি করতে হবে? ওটা কি স্যার এমনি করতে হবে? 4 pi p² dp টু দি পাওয়ার 3n করতে হবে?
হুম ইউ নো দ্য এন ডিমেনশনাল সারফেস কি করে করতে হয়?
হ্যাঁ হ্যাঁ স্যার, স্যার হ্যাঁ হ্যাঁ স্যার ভুল হয়েছে স্যার।
হুম
হ্যাঁ স্যার ঠিক আছে।
Urgen Lama, are you in touch? Urgen Lama? লাইনে দেখতে পাচ্ছি কিন্তু কিছুই শুনতে পাচ্ছি না। উর্গেন উর্গেন লামা। সুমন, সুমন is around. সুমন করছো? আচ্ছা করো করো করো। Okay. অভিষেক হলো না এখনো?
স্যার হয়েছে।
কে বললে?
স্যার দিব্যেন্দু।
দিব্যেন্দু? হ্যাঁ দিব্যেন্দু,
হ্যাঁ
ওকে।
স্যার।
হ্যাঁ কি হয়েছে বলো তো একটু।
স্যার
ওইটা তুমি
ওই
তুমি তুমি একটু প্রেজেন্ট করতে পারবে ওটা? তুমি
হ্যাঁ
যেটা
স্যার
করে।
আমরা তো জানি ডেনসিটি অফ স্টেট যেটা হয় জিইডি
না না
জিপিডি।
না 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 সেটা ঠিক আছে, তুমি যেটা করেছো সেটা একটু প্রেজেন্ট করো না। আমি বেরিয়ে যাচ্ছি প্রেজেন্টেশন থেকে। দিবেন্দু তুমি প্রেজেন্ট করে দাও এটা। তুমি প্রেজেন্টেশন মোডে যাও। হ্যাঁ, ওইটা ছবি তুলে নাও, তুলে নিয়ে হ্যাঁ হ্যাঁ। আচ্ছা, আর কারু হয়েছে? মৌসুমী, তোমার হয়েছে?
স্যার বলছি আমি যেটা মানে করলাম আমি বুঝতে পারছি না ঠিক, মানে যেটা জিইডি এক্সপ্রেশনটা বের করেছেন না ওইখান থেকে জাস্ট জি নিয়ে ভিটা ভাগ করেছি, তাছাড়া তো
হ্যাঁ
কিছু আলাদা কি
হ্যাঁ,
কিছু করতে হবে
না,
সেটা বুঝতে
ইন টার্মস অফ এনার্জি বের করেছো তো?
হ্যাঁ মানে ওটা
হ্যাঁ,
আমি মানে ক্যালকুলেশন করে আসলে করিনি, আপনারটা তো দেখলাম হচ্ছে জিইডি টা পর্যন্ত বের করা আছে, তো ওইখান থেকে
ওটা তো
জাস্ট
ওটা তো না, ওটা তো সিঙ্গেল পার্টিকেল ইন 3D। কোথায় বলো তো, কোথায় করা যায়?
শেষেরটা আমি ওটাকে এন পার্টিকেল ভাবলাম, তাহলে গন্ডগোল করেছি, আমার হয়নি sir।
না না, এন পার্টিকেল, এন পার্টিকেল।
হ্যাঁ।
দিবেন্দু, প্রেজেন্ট করো।
হ্যাঁ
দিবেন্দু,
স্যার,
হ্যাঁ প্রেজেন্ট করো।
আমিও স্যার সিঙ্গেল পার্টিকেলটা করেছি ওই জন্য।
ও না, আমি যে বললাম এন পার্টিকেল ইন 3D, আমি তোমাকে যে কোশ্চেনটা দিলাম।
স্যার করছি।
আচ্ছা ঠিক আছে, ছাড়ো। এবার তোমরা বাড়িতে করো, হ্যাঁ, কারণ এবার অনেকেই হয়তো বেড়াতে যাবে, অলরেডি বেরিয়ে পড়েছে এখান থেকে। হ্যাঁ, 2-4 জন, তোমাদের এখন খেলার সময় ইত্যাদি। হ্যাঁ, আমার মনে হয় যে লেট মি কুইট। হ্যাঁ, তোমরা একটু করে নিও, হ্যাঁ, খেলাধুলা করে এসে যখন সন্ধ্যাবেলা আবার বাড়িতে ফিরবে তো করে নিও, ঠিক আছে?
ওকে স্যার।
ওকে ওকে।
ওকে স্যার।